Hi everybody, so I'm going to finish up a problem I didn't get to in class, and then you're going to have another video tutorial that shows you other examples before you start trying more problems on your own. So use these as guides when you see something similar again. So in this civil engineering problem, it's a common one and it's an important one. We're trying to support, let's say, an overhang, this represented by this beam, and maybe we add to it a sign, a light, or whatever, and then we have to support it. And you normally support something like that by anchoring it into the wall, but that puts a lot of stress and strain on that anchor, especially if you're using even large bolts, anchors, whatever. So we're going to put a guy wire on there. And so what we want to find out is what's the tension on the guy wire. So the natural place you'd want to start is looking at balance of forces. So we do a force diagram. All right, so let's do that. And there are four forces here. There is a tension. Okay, that should be pretty clear. And I'm going to immediately right now take that tension vector and break it up into a vertical component. And I'm going to call that Ty, and I'm going to make it a horizontal component. Whoops. And I'm going to put it up here above that just for convenience sake. So there's my Tx. And I'm going to just switch the angle of 40 degrees up to there because I'm going to need that later. I want that in my triangle. All right, I have a force of gravity here. I'm just going to call this F2. I have the weight of the beam itself, and this is what's important about this force diagram we saw earlier, is we want to draw the weight vector where it's acting, and it's acting at the center of mass of that beam. So I'm going to call that F1. And then we can't forget that there is a force at the place where it's anchored. Right? We can see if the Tx is pulling to the left, there has to be some force to the right because the beam is clearly not accelerating to the left. So that's going to come from this. And this is not just pushing to the right, it could also be pushing up or down. So we're not quite sure whether it's pushing up or down, so I'm just going to take a guess and it will work itself out later. So what I want to understand is there's definitely a force there. I'm going to call it just a generic F. Okay? And there are components to it. There is an Fx, as talked about, and I'm guessing that the Fy is up. If it's not up, it will turn out as a negative value when I go to solve for it. Okay, so now what do I do with this? Well, everything's in balance force-wise, so let's make a algebraic statement of that. So in the x direction, it's fairly straightforward. I can say Tx minus or equals Fx, right? They're equal and opposite. Actually, I'm going to not put an equal sign there. I'm just going to put a colon. There's my statement. And I'm going to adjust this for Tx in terms of the tension, T, and the angle. So Tx, this would be T cosine 40 equals Fx. Okay, so if I ultimately want to find T from this equation, I need to know Fx. Well, I don't know Fx, so I'm kind of stuck there. So I'm going to go to my verticals. And again, I'm going to make this a colon rather than an equal sign. So for my verticals, I've got 1, 2, 3, 4 verticals. 2 are up, 2 are down. So I'm going to say Ty, and I'm just going to call that T sine theta here, plus Fy equals, right, M1g plus M2g, right? Those are the two gravitational forces, and because we're given the masses. And again, if I want to solve for T, I know this, but I don't know Fy. And I don't have an angle with Fy. I have no idea what angle it's acting, so I'm stuck. So I have 3 unknowns, T, Fx, and Fy, and only 2 equations based on balancing of horizontal and vertical forces. So how do we get around that? Well, if you have 3 unknowns, you need to have a third equation. Okay? I think in this next line has an unknown, which I just reiterated, and there are 3 overall. So in order to get a third equation, we're going to apply the second law for the torques. Okay, so not only are the forces balanced, the torques must be balanced because clearly that sign is not rotating. And it wants to rotate, and it will rotate because there are torques that are trying to rotate it, but they must be in balance. So now I'm going to look at clockwise and counterclockwise torques. So next to my forces, I'm going to label if there is a tau, kind of like we did before. So I could start, let's say, right here with Fx or Fy. Is there a torque associated with them? And the answer is no, because both lines of forces pass through our pivot point. So if we haven't established it already, there's our pivot. Okay. So no torques due to F or Y. Is there a torque due to F1? Yes. So that is it's trying to rotate it this way, so that's clockwise. F2 is also a clockwise torque. And so why isn't it rotating clockwise? Because Ty is giving us a counterclockwise torque, right? In other words, it's trying to rotate it up this way about the pivot. Then we can ask about Tx. Is it trying to give a torque? Now I've drawn the vector right here, but technically the tension is acting right there. And if I follow my line of force, it passes essentially through the pivot point. So there's no torque due to Tx. So make sure you're convinced of that, and you can see why it is, because it can be very misleading to think that there's a torque due to Tx because of where I drew the vector. But technically the vector is acting down here, so perhaps I should have been more careful when I drew that so it doesn't lead to a misunderstanding, if you will. Okay, so now we want to come up with our equations for the torques. So our clockwise torque is due to these two, so that's going to be, I'm just going to do it in a generic M1 G, and then our lever arm for M1, I know this is getting kind of busy here, is right there, right? That's R1, which is equal to the center of mass distance to the pivot point. So I'm just going to call that R1 for now. We can put in numbers later. That's the only, plus M2 G R2, and that's the lever arm for this one, and that's going to be the distance from here to there. There's our R2. The counterclockwise torque is due to Ty, and Ty is T sine theta. And then I got to multiply again by a lever arm. And that's just, I know this is really getting messy, that's just the length of the beam. So I'm going to call that R3, just to be consistent. Okay, so now what do I know? I know those two sets must equal each other. And here's the thing, and I'll let you fill in the details there. We know theta, that's given. We know R3, R2, and all that. In other words, we can solve for T. So ultimately, we don't depend on these to get us the tension because of that Fx and Fy. But since Fx and Fy don't show up in our torque equations because they pass through the pivot point, we can solve for T directly. So once you solve for T here, then you can use it and solve for Fx and Fy by plugging them back into those equations, and I want you to do that. Okay, I will post, let me do that, and let me write down the solutions. All right, so when I plugged in the numbers, for the first torque due to the beam, I get a large value, which I'd expect. It's a large mass. Make sure you put in 2.5 for your lever arm. For the hanging sign, it's a much smaller torque. Even though it's a bigger lever arm, it's not very much force. And then when I put in 5 meters for R3, theta's 40. When I solve it, I get about 4,300 newtons. I take this value, put it into this equation right here, and I solve for Fx. I get 3270 newtons. And then I do the same thing for this equation and solve for Fy, and I got a positive 2645 newtons. So the positive tells me that I guessed right, that the component of Y is upward. Okay, so the key lessons here. When you go to look at this mess on here and look at how do we figure things out by balancing, doing forces is not enough. Okay, that's not always going to be the case, but in this case, because of that F force, we have too many unknowns, and we have no real way of knowing what F is based on the other forces. Secondly, we can figure out the tension on this, the unknown, using balance of torques. We don't even need the balance of forces for that. The reason we ultimately need this is to find out the value of that F force. So you want to understand that conceptually. Okay, so that's the last of our example problems. You'll see more for different situations.